So the main point is that black holes have, as many of you are well aware, black holes have a natural size, which is set by the size of the horizon. So it turns out that if you have a light particle of the mass of that whose Compton wavelength is close to that size of the black hole, it will affect the evolution of the black hole through something that is known as black hole superradiance. And it will change the evolution of astrophysical black holes if a particle is in the right mass range. Now, before I tell you the physics behind this effect, I would like to give you a motivation why these types of particles, these types of bosons, very light bosons, are good things to be looking for through black hole superradiance. Now, so such particles arise naturally in many extensions of beyond the standard model physics. Perhaps the most famous ultralight boson is something called the QCD axion, which was proposed more than, now it's almost more than 40 years ago, to explain an existing problem in the standard model. Now, in the standard model, you can write a term that in the Lagrangian that essentially mixes the electric field of the strong interactions with the magnetic field of the strong interactions. So this is a term that violates parity symmetry, and it also violates charge CP symmetry or time invariant symmetry. So the effects of this term are parameterized by this theta parameter. And if in the standard model, we know that CP is not a good symmetry. So we were expecting this angle here to be order 1, this dimensions parameter. And if it were order 1, it would predict an electric dipole moment for the neutron. We've looked for such electric dipole moment, but we haven't found it. In fact, the only thing we've managed to do is constrain this theta parameter to be less than 1 part in 10 to the 10. So this has been a problem for a while. And back in the late 70s, early 80s, Frank Wilczek and Pechet Quinn proposed that promoted this theta parameter into a dynamical variable, which they called the axion. And the cosmological evolution of this field naturally relaxes this value of theta parameter to 0. So that explains why we haven't seen any EDM for the neutron. This axion is a particle that gets its mass from non-perturbative QCD effects, and its properties are uniquely characterized by what is known as the axion decay constant, Fa. So if this Fa constant is close to the Gutt scale or Planck scale, that is around 10 to the 17 GeV, you see that the Compton wavelength of this particle matches, is similar to that of the size of stellar mass black holes. The other thing to know about this particle is that it's also an excellent dark matter candidate, and there is a whole array of particle physics experiments that are being built, that are currently being performed, and have been proposed to look for it. So this is a way through this particle. This is a way with which black hole physics connects with particle physics searches. Now, this connection becomes even more clear if one extends the theory of the standard model, if one looks at even bigger extensions of the standard model, such as string theory. So turns out that string theory has 3 fundamental ingredients. It has extra spatial dimensions that are needed to make the theory mathematically consistent. There are fields, there are particles that live in these extra dimensions, and there is topology. These extra dimensions cannot remain large. They need to be compactified to give rise to our 4-dimensional world. And they can be compactified simply on a sphere or on a torus, or in fact, the only thing that limits the type of compactifications you can have is the imagination of the person that writes that said compactification. So the shape of this compactification, the shape of this extra dimension, is also known by topology. So it turns out these three fundamental ingredients, so these extra dimensions, when compactified with non-trivial topology, the gauge fields that live in these extra dimensions will manifest in 4 dimensions as extremely light particles. They're going to be nearly massless. So these are going to be particles that are much lighter than any of the known particles of the standard model. And presumably some of them you can imagine being in the range that's relevant for astrophysical black holes. There are these particles are bosonic in nature. So they can be spin 0, and they are CP-odd particles, just like the QCD axion that I mentioned before. They can be spin 1 particles, which basically have similar properties as the ordinary photon. And they're also CP-even scalars. And these come from the fields that determine the shape and size of this extra dimension, as well as the value of the fundamental constants that we measure in our 4 dimensions. So they go by the name of dilatons, moduli, and the radiance. So this is a large class of bosonic spin 0 and spin 1 particles that are perfectly self-consistent. They are motivated by well-known extensions of the standard model, and by construction, they are coupled to us extremely weakly. So it's easy to imagine that they only couple through the force of gravity, and they are extremely light. Now, all of these are excellent dark matter candidates. So there is, as I mentioned previously, there is an entire array of experiments that is currently being conducted and proposed to look for this type of particles. So the way you would look for them depends on how this particle couples. So axions, in the presence of an external magnetic field, will convert to photons. This is the idea behind the ADMX experiment, which is located at the University of Washington, and it promises to be the first experiment to probe the QCD axion in a laboratory setting. So far, we've only been constrained these particles, basically the QCD axion only through astrophysics. Axions also couple to spins. So you can look, for example, the precession of particles with spin, either electrons or nuclei, as they move through in a dark matter, axion dark matter background. Now, dark photons, the spin 1 particles that I mentioned earlier, can mix with the ordinary photon, and as such, they can be detected with the same techniques you would try to detect ordinary photons. Of course, you have to shield every standard model background. So, for example, the idea behind the dark matter radio is that you take a photodetector and put it inside shielding. Ordinary photons will stay out, but dark photons, if they are the dark matter, will penetrate this volume, and you will try and you can detect them. Now, moduli, the things that determine the shape of the extra dimensions in string theory, can actually cause, if they are the dark matter, can cause oscillatory variations of fundamental constants. And you can look for them in atomic clocks and atom interferometers, as well as resonant mass detectors. And this is another array of experiments. So this is an entire array. There is, as I said, there is many experiments that are currently being conducted. But the main takeaway of these particles is, first of all, they are very well motivated. They are excellent dark matter candidates that can mediate new forces. And now, something that's completely model independent, and this is where black holes come in, they can affect the evolution of black holes independently of how they couple to us, only through the universal force of gravity. The interesting thing is that besides a tool, this way, black holes comes into our hunt for beyond the standard model physics in a highly non-trivial way. They can help us discover things like the QCT axion. And at the same time, if you discover more than once, the interesting thing is more than one actions, for example, it would be evidence for the complexity that you see in string theory, and of course for beyond the standard model physics. Now, I would like to spend the rest of the talk explaining to you how exactly black holes are good for looking for these ultra-rarite particles, ultra-rarite bosons. And I need to stress that for the rest of the talk, you won't care if this particle is the dark matter or not, and you also don't care really how it couples to us. All you care is that there is an ultralight boson that's in the right mass range, and it couples to us through the force of gravity. Okay? So the effect that's relevant for this is the effect of superradiance. And this is something that is not special to black holes. So in order to explain to you how this thing works, let me give you a toy example. So imagine you have a rotating cylinder, okay? And you take a ball and you scatter it tangentially from the cylinder. Now, if at the point of contact, the ball is moving faster than the cylinder, then the ball will come out with less velocity than what it came in because of the force of friction. But now imagine that you speed up the cylinder. At the point of contact now, the cylinder will be moving faster than the ball. So then what will happen is because of the force of friction, the ball will actually be given a push from the cylinder. So it will have higher velocity than what it came in with. Now, a similar thing can happen if you have waves. Now, the relevant thing here is comparing the angular velocity of the cylinder with the angular velocity of the wave. And the cylinder here for waves, the type of waves that we know of can be, of course, gravitational waves. It can also be photons, light. And for light, the cylinder needs to be made out of material with finite resistivity, because this is what gives the analog of the friction force. So if you take a rotating conducting cylinder and you scatter an electromagnetic wave from it, if the angular velocity of the cylinder is larger than the angular velocity of the wave, then the wave will come out amplified, okay, from the scattering process. This is what is known as superradiance scattering, okay? Now, in a similar thing happens for black holes. Sometimes it's referred to as Penrose process, but I think given how general this process is, this may not be the best name for it. Now imagine here the black hole has a horizon, okay? So this is what plays the role of the absorption. So, and there is also an ergo region that signals, basically, it's the metrics way of saying that the black hole is spinning. So if the angular velocity of a black hole is larger than the angular velocity of a wave that scatters from it, then the wave can come out amplified. And this is a process, in fact, I should say, that extracts energy and angular momentum from the black hole. Now, back in 72, Press and Tukowski wrote a very nice paper where they say, well, let's repeat the scattering experiment, but now let's surround the black hole by a perfectly spherical mirror. So when you do that, the wave gets amplified by every single reflection. Eventually, the amplitude grows exponentially. And because of the larger radiation pressure, the mirror can explode. So this is what they, in a very cute way, they call the black hole bomb. Of course, this is in no way a realistic scenario that you can construct out of ordinary photons or gravitational waves. Now, the thing is that if you have the key point, though, here that that was missing in this picture is that, first of all, it's clear that you need bosons to do this. There is no enhancement for this exponential enhancement cannot happen for fermions because of Pauli's exclusion principle. And the key point is that for the photon and the graviton, they don't have a mass. So if you have a mass, the mass acts like a mirror that creates a bound state with a black hole. And what you will see is now that formally what you see is that there is, in the Klein-Gordon equation, there is an instability. So if you have a black hole that's rotating, and there is a particle that has a Compton wavelength that's similar to the size of the black hole, doesn't have to match the size of the black hole, then what you will see happening is that you will have exponential growth of the occupation number of particles in a bound state around the black hole. And the black hole will spin down, okay? Now, this still looks a bit like magic, but it becomes easier to understand if one thinks how these bound states look like. So unless you sit very close to the black hole, the potential that the particle sees is a 1/r potential, a Newton's potential. So when you solve for the bound states, you found that the wave functions for a scalar look very similar, exactly the same, very similar to those for the hydrogen atom. So you can define a fine structure constant, which is Newton's constant times the mass of the black hole times the mass of the particle. And you can define also a principal, orbital, and magnetic quantum numbers for each of the levels, and you find that there is the analog of the Rydberg formula. So the energy goes like alpha squared, the fine structure squared, times the mass of the particle over the principal quantum number squared. Now, and this is a great tool for understanding how these states look like. Now, there are very important differences between what this gravitational atom in the sky looks like and what the hydrogen atom is. So first of all is that of size. These are things that are kilometers or billions of kilometers large. The other main difference is that instead in the hydrogen atom, the electrons are fermions. So what occupies the levels of the hydrogen atom is determined by Pauli's exclusion principle. Here, you have bosons. And bosons, because of this instability, can grow to huge occupation numbers. In fact, if you count how many particles there are in these bound states in the final state of the superradiance, you will see that you will have more than 10 to the 77. Basically, it's more particles around in these bound orbits that there are protons in all the stars in the universe. So this is a very highly occupied state, and as such, it shouldn't be thought of as a particle state or a quantum state. Is a very classical wave state, okay? Now, the other important thing is that the system, when you solve the equations, the Klein-Gordon equations in a curved background versus the hydrogen atom, for the hydrogen atom, you have to impose that the wave function is regular at the origin. Here, because of the presence of the horizon, you have to impose ingoing boundary conditions at the horizon. So this changes what was supposed to be a Hermitian problem in the case of the hydrogen atom to a non-Hermitian problem. So that means that when you solve for the eigenvalues, you will see that these eigenvalues have a small imaginary number. And this is the rate of the instability. So what you see, so not all levels have an imaginary number that can grow. In order for these levels to be unstable to growth, you need to satisfy the superradiance condition. And basically, the frequency of the axion in this bound level, which is the mass plus the binding energy, has to be less than the magnetic quantum number of that level times basically the angular velocity of the black hole. And it connects with what I said before, because omega over the magnetic quantum number is essentially the angular velocity of the wave. Okay, so you see here, first of all, that this superradiance condition is a kinematic condition. So there is no need for resonance, meaning that the particle Compton wavelength does not need to match exactly the size of the black hole. So a single black hole can probe a large range of masses. Now, as I said before, this is a universal phenomenon and should not be thought of as special to black holes. So what, of course, for the next question to ask is, okay, it's not particularly tuned to get this instability, but how fast does it happen? Does it care about any of the, how does it compare to regular astrophysical processes? And that is determined by superradiance stability rate. And for spin zero particles, it's roughly 10, can be as fast as 10 to the 7, the gravitational radius of the black hole, or the infall time, if you wish. So for a stellar mass black hole, this corresponds to a time scale of 100 seconds. Now, for a spin one particle, this can be even faster, and the instability can occur in something like even less than 1 second. Okay. Now, these time scales are indeed long compared to the infall time, but the relevant time scale for the evolution of astrophysical black holes is the accretion time scale, which is 10 to the 8th year. So this is why, so astrophysical black holes have a very long evolution time scale compared to these instability rates. So this superradiance has enough time in astrophysical setting to affect the evolution of astrophysical black holes. And depending on, so this is the optimal time scale. So if the particle becomes heavier, then this time scale becomes exponentially long. And if the particle becomes lighter than this optimal condition, then you see that the time scale goes like a power law in this fine structure constant that I mentioned before. So in order to understand how the superradiance will evolve for a realistic environment and for a boson, first of all, you need to take into account the superradiance stability rates. You need to take into account the black hole evolution, meaning the accretion, mass, and both mass and accretion rates. You need to take into account dynamics between in this gravitational atom. So for example, because the levels are quantized, you may have gravitational wave transitions between levels. The interesting thing about, in particular, axions and dark photons is that they are their own antiparticles. So you also get gravitational wave emission from bosons annihilating in the cloud. And finally, there are interesting things that can happen. These are the first few effects that I talked about only depend on the force of gravity, but interesting phenomenology can arise if there are self-interactions between these particles or if there are interactions with the environment. And I will talk about them later. So the first thing that you would expect to see or not to see if there is a boson in the right mass range that can affect the evolution of astrophysical black holes is that those black holes won't be rotating fast, okay? So this is a plot that shows the dimensional spin of the black hole as a function of the mass for a specific axion, for specific, here I'm talking about scalars, particular axion, so this mass is 10 to the minus 11 eV. So everything that is in blue could be affected by superradiance. And different levels of this gravitational atom will be responsible for slowing down black holes at different regions. So what you would expect to see, the first thing you would expect not to see is any black holes in the blue. All black holes, if there is an axion in the right mass range, it should be in the white region. And the interesting thing is that we have actually measured spins and masses of stellar mass black holes in particular. And those already place constraints in here for axions, and in particular for the QCD axion that I mentioned before. The interesting thing is that this is a mass range that is extremely hard to probe in a laboratory setting. Okay, so in particular for the QCD axion, black holes place the only constraint that we know of in this part of its parameter space. Now, if you combine measurements and you look at the spin 1 particles 2, you'll see that there is an entire range that is constrained. So there are also constraints coming from supermassive black holes, for spin of supermassive black hole measurements. And there are also different for axions, but there are also constraints that come from vectors if you do a similar analysis, and those are more stringent because vectors cause a faster superradiance stability. Now, turns out that if you have self-interactions, that affects the evolution of the instability. And in fact, at very large self-interactions, these self-interactions will inhibit the growth of the instability. So this is a plot that kind of shows this. This is the inverse axion decay constant here on the y-axis. So here, as you go to larger values, here you have larger self-interactions. At the bottom, you have the mass. And these are the same, kind of the same data points that I had in the previous plot, taking into account the fact that the possibility that you can have self-interactions. Now, I would like to point out this purple region here, because this is a constraint that just got published, and it actually comes from LIGO data, okay? So as I said in the beginning, now if you were to plot spin versus black hole mass, and you had a particle, a boson in the right mass range, there should be forbidden regions because of the superradiance effect, and you should see all black holes here, as you see in the pink region, but nothing in the white. Okay, so that can affect basically the spin distribution. If there is a superradiance happening, will affect the spin of merging black holes, the spin distribution of merging black holes. So the fact that for events that LIGO has measured, we have even ever so a bit bad measurements of the spin of the black holes, that can actually place a constraint in this mass range between basically a factor of 2 in mass range, around 10 to the minus 13 eV, that is complementary to the X-ray binary data that I showed before. So this is something that a new analysis on LIGO data, and this will improve. This is just the beginning, because LIGO will keep getting new data. With upgrades, the sensitivity will improve. So this shows not only that there is future in these searches, but there is a lot of useful physics that we can extract from LIGO data now, from gravitational wave data now. Now, perhaps the most, the extraction of spin is in a way an indirect effect. It doesn't tell you that if a cloud is there, if a superradiance cloud is around the black hole. So so this brings us to perhaps the most spectacular signature of the black hole, which is monochromatic gravitational wave emission. So if you have a cloud of particles bound around the black hole, and in the case of axions, as I said, and dark photons, they are their own antiparticles, so they can annihilate to a single graviton with basically energy of twice the particle mass. And this is a very, this is of course kind of Bose enhanced emission. And this is a very monochromatic gravitational wave source. okay? And this gives you, this 10 to the minus 22 gives you the characteristic strain that you would expect to see if you have a source, a cloud, that's 1 kiloparsec away from us. Now, the signal, how long the signal lasts, depends on the annihilation rate. And for stellar mass black holes, this can last for thousands and thousands of years. So in order to see the potential, back in 2014, 2015, we did an analysis which was basically pre-advanced LIGO then, where we assumed a certain black hole distribution, we assume a certain spin distribution, and the point is that in the galaxy you can have up to 10 to the 9 roughly black holes that are isolated. They don't have to be in binaries. So this is the number of monochromatic gravitational wave of sources you would expect to see based on different sensitivities of advanced LIGO type, advanced LIGO and future upgrades of advanced LIGO as a function of the mass. So, so this is the band that you see. So you see here that you can see up to, if you're very optimistic about the spin distribution, the birth spin distribution of black holes, you can see here that you can see thousands of monochromatic gravitational wave sources if you have an action in the right mass range. Now, so the interesting thing is that this analysis basically now almost 2 years ago, a year and a half ago, was done by the Hanover group. And here, this is a similar plot that comes from actual advanced LIGO data. This is another search that is currently ongoing and shows great promise for the future. An interesting thing that it's not necessarily connect with gravitational wave detectors, but it's complementary in some ways. So if you have self-interactions that change the evolution of the system, they can also be the source of monochromatic scalar waves, bosonic waves, matter waves from the cloud. So you can actually have signatures in experiments that are designed to look for dark matter. So in a way, there is complementarity, and also this is the analog of multi-messenger astronomy for this type of searches. Now the question is, for the last few minutes, I would like to address the questions. Okay, this is great. What remains to be done? It looks like there's already many ongoing searches. There's tons of stuff that have already been said. Turns out there is still a lot of work to do. So from the theory aspects, the signatures and the prospects of looking for signatures of superradiance in extreme mass ratio in spirals has not been fully studied. Even though Daniel Baumann has written in the last, I think it's now 3-4 years ago, a very interesting paper that discusses aspects of how a cloud around a supermassive black hole should behave when there is an infalling star towards the black hole. We need to do so. The self-interaction signatures that I talked about have only been done in an analytic regime. In order to see their potential properly, you need proper simulations. This is for spin 0 particles. For spin 1, similar things need to happen. Now, the thing about spin 1, there can be, because spin 1 particles, dark photons can have a mixing with the ordinary photon. They can create a huge electric field in the environment of the black hole. That can have huge effects in the way this electric field interacts with the plasma around the black hole. You have strong electromagnetic field processes that become relevant and can be a huge source of energy around the environment of the black hole. So this is something that people have not really studied yet and could give extremely interesting signature, because I didn't mention this, but in fact, the cloud around the black hole can carry a significant fraction of the black hole mass, up to a few percent. So there is a lot of mass, that means energy stored in the cloud. And some people have talked about spin 2, black hole superradiance. I don't think the motivation for such particles is as strong as it is for spin 0 particles and spin 1 particles. Now, I talked about monochromatic searches. I should point out that there is also this annihilation of particles can be a source for stochastic gravitational waves that are more relevant for lower frequency gravitational wave detectors. Now, for all of these searches and the signatures that are presented, we were making assumptions about the black hole spin and mass distributions. So in some ways, not always, in some ways, all the constraints that we derive depend on the statements, assumptions we make about the black hole spin and black hole mass. So the more people understand how black holes are formed, with what spin, and what happens in binaries, and how they evolve in an astrophysical setting, the more will give us about how well about the phenomenology of this effect. So I hope I have given you an idea of how black holes can be already probing interesting parameter space for ultralight bosons. And the interesting thing is that and this is only through the force of gravity of these particles. And what I find exciting is this is an important beyond the standard model direction for gravitational wave searches, that at the same time connects with a wide class of experiments that we do in a laboratory setting in the field of particle physics experiments. So for me, the future is bright with this. And whatever we learn, even if it's not positive, it's extremely instructive. Thank you.